Start.
Okay, sir. Hello, everyone, and thank you for joining us in today's conference. I, Dr. Saloni Shrivastava, welcome you all in the inaugural session of today's International Conference on Advances in Applied Sciences, Humanities, and Technology to Overcome the Global Disasters, organized by the Department of Applied Sciences, Mathematics, Raja Balwant Singh Engineering Technical Campus, Bijpuri, Agra, in association with Institution of Engineers, IEI, Agra Local Center. Before starting our inaugural session, I request you all to keep your audio and video in off mode, and also do not share your screen in between. To start our inaugural session, I would like to request Vice President of the conference, Professor B.S. Kushwaha sir, Director, Raja Balwant Singh Engineering Technical Campus, Bijpuri, Agra, to deliver his welcome address. Sir, please.
I'm audible.
Yes, sir.
Our distinguished chief guest, Honorable Professor R.K.S. Bhadre, Vice Chancellor, MS Bridge University, Bharatpur. President of this inaugural ceremony, Honorable Yuvraj Amritpal Singh Ji, Secretary Balwant Education Society. Guest of honor and Chairman ICAI Agra Local Center, Dr. Ashok-Yadav. Guest of honor and keynote speaker, Dr. M. Yasin Jubail from Saudi Arabia and Dr. Jerry Lloyd Bona from University of Illinois, Chicago. Professor Pankaj Gupta Ji, Director Administration and Finance. Coordinator of the conference, Dr. Sashpati Pandey Ji. Co-coordinator of the conference, Dr. Amit Kumar Singh Ji. Participants from India and abroad, ladies and gentlemen, good morning to all of you. I, Professor B.S. Kushwaha, Director Raja Balwant Singh Engineering Technical Campus, Bijpuri, Agra, and Vice President Organizing Committee, welcome you all in the International Conference on Advanced and Applied Sciences, Humanities, and Technology to Overcome Global Disasters. History of the college was started in 1885 when college was started in the form of a small boarding house of 20 students. The Faculty of Engineering and Technology, RGS College, Bijpuri, Agra, was started in the year 1996, and currently we have Faculty of Engineering, Faculty of Architecture and Town Planning, and Faculty of Pharmacy. We have 8 BTech programs and 4 MTech programs along with the DPharm and BPharm. The courses are approved by AICTE, PCI and Council of Architecture, New Delhi, and affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. I am sure that the presentation and discussion during this international conference will be highly beneficial for young researchers and senior scientists. From different countries. At the same time, I am also hopeful that the recommendations of this international conference will play an important role to overcome global disasters. Once again, I welcome you all and this international conference a grand success. Thank you very much. Thank you very much. Over to organizer.
Sir, now I would like to request coordinator of the conference, Dr. S.P. Pandey sir, Department of Mathematics, Raja Balwant Singh Engineering Technical Campus, Bijpuri, Agra, to deliver his lecture on about the conference.
Thank you, Madam. Respected President of this conference, Yuvraj Amritpal Singh Ji, Secretary Balwant Engineering Society, Chief Guest, Honorable Vice Chancellor, MS Bridge University, Professor R.K.S. Rathod ji, R.K.S. Dhakre ji, Guest of Honor, Chairman IAI Dr. Ashok Yadav ji, respected Director Professor V.S. Kushwaha ji, respected Director Admin and Finance Professor Pankaj Gupta ji, Guest of Honor and Keynote Speaker Dr. Jerry Lloyd Bona from University of Illinois Chicago, Guest of Honor and Keynote Speaker Dr. M. Ziauddin from Industrial College, Saudi Arabia, dignitaries and all participants. I, Dr. Sachipati Pandey, welcome you all in this 2 days international online conference on advances in applied science, humanities and technology to overcome global disasters. Organized by the Department of Applied Science, Mathematics, Raja Balwant Singh Engineering Technical Campus, Bijpuri, Agra, in association with Institution of Engineers, India, IAI, Agra Local Center. Before giving the overview about the conference, let me introduce my Department of Applied Science Humanities. It is a department that provides an enduring foundation in the fundamental sciences. The purpose of applied science in engineering study is to lay a strong foundation of basic principles of various disciplines such as mathematics, physics, chemistry, and communication skills in the mind of the learners so that they proceed to rest of their years of study with up-to-date knowledge and training of basic engineering skills. Mathematics departments take the initiative and also made the best arrangements for this 2 days international e-conference through their extraordinary hard work and sincere dedication. Now I would like to give an overview of this conference. A natural disaster is a major adverse event resulting from natural processes of the earth. Examples are floods, hurricanes, tornadoes, volcanic eruptions, earthquakes, tsunamis, storms, and other geological processes. A natural disaster is an event that is caused by the natural forces of the earth and result in great damage and the possible loss of life. Each year, the earth experiences natural disasters. When natural disasters occur in heavily populated areas, a lot of people may lose their lives. A recent example is the dealing with the unforeseen challenges caused by the COVID-19 pandemic has taken a significant toll on people all across the world. The pandemic has impacted the lives of people all across the world. The pandemic has impacted the lives of people all across the world. Nevertheless, the recent study assessing the likely number of COVID-19 deaths in the country suggests that the virus may have hit even harder than the authorities initially thought. Scientific and technological solutions to the complex problem of disasters must be rooted in social realities in the fullest sense of the term. Science needs to be seen as part of a continuum of action extending from the design of interdisciplinary research to the communication of results to diverse non-specialist user groups. In this vein, scientists will have to share with policymakers and others the responsibility for scientifically sound risk assessment and management. Without science and technology and their blending with other disciplines, there can be no world safer from natural disasters. Thanks to science and technology, we already know much about natural hazards and about the ways and means to avoid or reduce many of the effects. This is what the aim of our 2 days international conference is. In this 2 days international conference, we are going to have 4 technical sessions. The first technical session is going to start at 12:30 to 2 p.m. In this, we are having the invited speakers as Professor Ramapati Mishra from RML Awadh University, Faizabad, and Professor Sanjeev Kumar from Institute of Basic Sciences, Dr. B.R. Ambedkar University, Agra. And we have many more other participants who are going to present their paper in the first technical session. In the technical session 2, we have the invited speaker as Anubhuti Sharma. She is a senior scientist ICAR DRMR Bharatpur, and the rest we have about 40 to 15 papers in the session. In the day 2, in the 19th September, tomorrow, Saturday, the technical third session will start at 10 a.m. to 11:30 a.m. And the invited talk is of Dr. Devendra Kumar from IT Department, University and Technology and Applied Science, Shinaz Sultanate of Oman. He's from Oman. He's from Oman. And the second invited talk is of Dr. Tamal Basak from Amity University, Kolkata. And rest of the paper, many of the papers are also being presented in this session of third technical session. In technical session 4, in 4 technical sessions, we have invited speaker as Professor Sandra Pinilles. She is from Portugal, University of Mathematics, Department of Mathematics, Portugal. And the second invited talk will be of Dr. Ashutosh Kumar Singh, later from Asaram University, Lucknow. So this ends the 4 technical sessions of our conference, and the 4th session will end at 2 p.m. tomorrow. So now I am thankful to all the dignitaries who are sharing their precious time with us in this event. Thank you very much.
It is a great honor for me to welcome guest of honor of the conference, Dr. Ashok Yadav, sir, Chairman, IEI. I would like to request Dr. Ashok Yadav, sir, to deliver his address note. Sir, please.
Okay. Thank you, madam. Am I audible to you? Please let me confirm. Hello. Yes. Thank you very much. Am I audible?
Yes, you are audible, sir. You are audible, sir.
Okay. Thank you. Thank you, madam. Thank you for such nice introduction. I feel
Yes,
yeah?
sir. You are.
Okay. I feel proud and glad to be here to attend this international conference on advances in applied sciences, humanities, and technology to overcome global disasters. I must appreciate the efforts made by Department of Applied Sciences, Mathematics of RVS Engineering Technical Campus, Bijpuri, Agra. I have gone through your technical session schedule, and I am delighted to note that professors and researchers from all over the world are participating in this conference, which will definitely increase the level of this conference. I congratulate the director, Professor B.S. Kushwaha, and the Director Admin and Finance, Professor Pankaj Gupta of the Institute for organizing this meaningful educational event. I especially congratulate Dr. S.V. Pandeji, coordinator, and Dr. A.K. Singh, co-coordinator, for taking the initiative to organize this international conference. I also congratulate all the organizing committee members for their efforts. Now, I feel it imperative to speak about IEI very quickly. I will not take very much time. The Institution of Engineers, that is IEI India, is a statutory body to promote and advance the engineering and technology established in 1920 and incorporated by Royal Charter in 1935. It is the largest multidisciplinary professional body of engineers encompassing 15 engineering disciplines with a membership of more than 820,000 and serving the nation for more than 9 decades. The IEI has its headquarters located in Kolkata with national presence through more than 100 centers and several overseas chapters, forums, and organs. The institution was granted Royal Chartered on September 9, 1935 by Emperor George V, which was a momentous event in the annals of engineering industry and education in India. The Royal Chartered endowed the institution with the responsibility to promote the general advancement of engineering amongst members and persons attached to the institution. IEI has been recognized as scientific and Industrial Research Organization by the Ministry of Science and Technology, Government of India, and besides conducting its own research, provides grant in aid to UG, PG, PhD students of engineering institutes and universities. The Institution of Engineers India is a first professional body to represent India in several international bodies. The Institution of Engineers India is a pioneer body to introduce continuing engineering education program, successful completion of which is recognized as equivalent to a degree in engineering by Government of India, the Union Public Service Commission, the state governments, and many public-private sectors organizations in the country. The Institution of Engineers India, with its headquarters in Kolkata, is administered by the National Council with the President of IEI as its head. Ever since its inception, IEI has been the forerunner in setting up national standards for promoting the country's industrial base, which culminated on the formation of Indian Standards Institution ISI, now called as Bureau of Indian Standards, that is BIS. IEI, in collaboration with Springer, regularly publishes peer-reviewed international journal in 5 series covering 15 engineering disciplines. Once again, I congratulate all the members, committee members of the organizing committee for conducting such a profound event. Thank you very much. Over to you, madam.
Thank you, sir. Now it is my great privilege to welcome Chief Guest of the conference, Professor ICAASHTOGD-20, sir, Vice Chancellor, MS Bridge University, Bharatpur, India. Let me introduce him. He gave his contribution in academics in the form of Joint Secretary, Treasurer, General Secretary of Indian Council of Chemists, an organization of chemistry researchers having more than 2,000 live fellows and more than 8,000 floating annual fellows. Executive Editor of Journal of Indian Council of Chemists, UGC listed journal. He is also a member of various high-power committees of national and state level such as NAC, UGC, DST, Chairman Search Committee for VC Selection, Special Task Force on Higher Education, Rajasthan, Selection Committees of State Commissions, State, Central, Deemed, and private universities for teachers. He published more than 50 research papers in national and international journals, presented more than 150 papers in national and international conferences, seminars, and webinars. He supervised regular 45 MPhil dissertations and guided 31 regular PhD theses. He organized almost 38 national conferences, various seminars, and 7 international conferences abroad. He also visited many countries in his academic career. Sir, we are lucky that today you are with us. Now I would like to request our chief guest to deliver his address note. Sir, please.
Namaskar. Good morning to all. I am audible? I am audible?
Yes, sir, you are audible. Yes, sir, you are audible.
I am delighted. Okay, madam. I am delighted to participate in the inaugural ceremony of online international conference on advances in applied sciences, humanities, and technology to overcome global disasters today on 18th September. I greet the organizers, especially Dr. Professor B.S. Kushwaha, Dr. S.P. Pandey, Dr. Ashok Yadav, Professor Pankaj Gupta, Dr. Amit Kumar Singh, and their team members. Respected Yuvraj Amrish Pal Singh Saab, the President of the function, and Dr. M.J. Jubilee, Guest of Honor, and Dr. J.L. Bona, the keynote speaker and distinguished guest. I would like to start my address by mentioning 2 quotes. The first one is, right information enriches knowledge. Knowledge makes the nations great. And the other one is, ask not what your country can do for you, ask what you can do for your country. And the first one was saying of Dr. APJ Abdul Kalam, and second one is of John F. Kennedy, the president of USA. These are very well fit into the theme of today's conference. I'm sure the conference will give the opportunity for bringing about better cohesion of approach and better understanding of both objectives and expectations arising from the problem. The largest democratic nation, India, has survived various turbulences and disasters of all kinds over the last century and more. But our strength has always lain in overcoming those disasters and setting firmly on the road to higher and higher levels of efficiency and progress. I would like to suggest the organizers to run extensive campaign against the present disasters and create awareness among the society and to every concerned. I inaugurate the present international conference and my best wishes to all the participants for a great success in the mission of India as the most informed and participative society in the world. Jai Hind, Jai Bharat. Over to organizer Dr.
Thank you, sir.
Thank you, sir. Thank you.
Sir, I'm audible?
Yes, yes.
Thank you, sir.
Yes, madam, you are audible.
I find my immense pleasure in introducing our guest of honor and keynote speaker, Dr. M. Ziauddin Zubail, sir, Industrial College, Saudi Arabia. Dr. M. Ziauddin, sir, is presently working as an assistant professor in the Department of General Studies, Mathematics, Zubail Industrial College, Royal Commission, Zubail, Saudi Arabia. He did his master's in mathematics from the Department of Mathematics, Banaras Hindu University, Varanasi, India. He has completed his PhD in mathematics from IIT BHU, Varanasi, India. Before coming to Saudi Arabia, he was working as a postdoctoral research fellow at Joint Institute for Nuclear Research, Moscow, Russia. He has also worked in several universities in India. He has so far published about 20 research papers in the Journal of International Repute. He has delivered several invitee talks and presented papers in international conferences. He is a reviewer of several journals and a permanent reviewer of American Mathematical Society. Now I would like to request Dr. M. Ziauddin Zubail, sir, to deliver his keynote address. Sir, please.
Sir, unmute your mic, sir. Unmute your mic, sir. Mohammad Ziauddin, sir. Please unmute your mic. Now.
Thank you, sir. Am I audible now?
Now you are doing.
Yes, sir.
Yeah, thank you very much for introducing me in such a nice way. And first of all, I would like to thank the organizers for giving me this opportunity to deliver a lecture as a keynote speaker. So as I have already been introduced now, so no need to have formal introduction now. I'm directly coming on to my presentation. Now, yeah. So today I have tried my level best to make it more theoretical rather than more mathematical things should to be introduced now. So title of my presentation today is A Brief Introduction to Gravitation and Cosmology. Here I will just give an idea about the gravitation and cosmology. It will not take much time now because I have tried my level best to make it theoretical, more theoretical rather than mathematical. So this is the plan of my talk. First, I would like to discuss about the history of the universe, how the people, how time to time great astronomers, thinkers, philosophers and scientists gave the idea about the universe, its origin, its fate and everything, right from the beginning. Now, it's a little bit brief history about the universe. And then I will discuss about the gravitation and geometry of space-time. What is the relation between gravitation and the geometry of space-time? This is very interesting in Einsteinian theory, basically. And then after that, we will discuss about some motivation of the cosmological models. And then important cosmological model must be discussed, because these are very important things nowadays to be understood. So, now starting with the history of the universe, time to time great scholars, philosophers, thinkers, great scientists, they gave their ideas about the universe. And starting from, this is the chronology you can see, starting from the Aristotle, about 340 BC, he was the first person, to give the idea about the universe, how it is started, what was the origin of this, and what will be the fate of this. Starting from the Aristotle 340 BC, followed by the Ptolemy, 1st century AD, then Copernicus came, 1514 AD, then Johannes Kepler and Galileo together at the same time, and followed by the Newton in 1687, and then finally Einstein in 1970. Nowadays, the theory given by the Einstein is more appropriate, or we can say the absolute theory about the complete theory of, about the universe, the gravitational theory. That is theory of general relativity. Everybody knows about this. So now, starting with the history of the universe, Aristotle, as long ago as 340 BC, in his book on the heavens, was the first person who had given the idea for believing that Earth was a round ball rather than a flat plate. Observing the eclipse of the moon, he realized that shadow of the Earth on the moon was always a rod, which is possible only if the Earth was spherical. This was very interesting question, Finally, he talked about the geocentric nature of the universe. That is, the Earth was stationary, and the sun, the moon, the planets, and the stars moved in circular orbits about the Earth. And then Ptolemy, in the 1st century AD, elaborated the Aristotle's idea into a complete cosmological model. In Ptolemy's model, the Earth stood at the center, surrounded by the moon, the sun, the stars, and the 5 planets known at the time: Mercury, Venus, Mars, Jupiter, and Saturn. Both model was not universally accepted because the idea of the geocentric nature was not properly justified. Later on, in 1514 AD, Nicholas Copernicus, he was basically a polished priest. He was not a scientist. He was basically a thinker and priest. He was a priest at the time. Proposed a much simpler model of the universe, in which he talked about the heliocentric nature of the universe. That is, the sun is at the center of the universe, and the rest is moving around it. After a century, the Copernican theory was strongly supported by 2 astronomers. They were Johannes Kepler and Galileo Galilei. And we know about the Galileo Galilei now. What has happened with him now? He was brutally murdered because of supporting this idea. Kepler not only supported the Copernicus theory, but also modified it by suggesting that planets were moving in ellipses rather than in circles. The whole explanation about the elliptical orbit was provided by the Newton in 1687. Newton put forward a theory of how bodies moved in space and time by giving his 3 laws of motion. The very, right from the beginning, from our childhood, we are learning these 3 laws of motion. And also he postulated the law of universal gravitation, According to the law of universal gravitation, any 2 bodies in the universe, they attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance. This is a well-known universal gravitational theory. We all know about this. But Newtonian cosmology did not make progress, especially when applied over the distances of several thousand million light years. This theory, doesn't make progress for a large time. Later on, Newtonian theory was replaced by Einstein's general theory of relativity. And the modern cosmology found its greatest inspiration in Einstein's general theory of relativity. No. So these were the brief history about how the evolution of the universe came to the people's mind, how time to time great thinkers, philosophers, and astronomers, they gave their ideas about the evolution of the universe. So these were very interesting, because of these people, we came to know nowadays what human has the knowledge because of these people, these great, philosophers and scientists. Now I'd like to come on to the gravitation and geometry of space-time. This is the second topic that I want to discuss now today. So before just understanding the Einsteinian general theory of relativity, that is a complete theory of gravitation now, we have to understand few things more. Starting from the Newton's law of gravitation, in his famous book Principia in 1687, Newton discussed the laws of motion as well as of gravitation that we already discussed. Then Michelson-Morley experiment. This experiment is also very, very important. In 1887, the Michelson and E. Morley, through their famous experiment, have recognized the light wave as electromagnetic in nature. This was a drastic discovery in the field of astronomy and the cosmology. He also put forward the ideas of no absolute motion and the constancy of the velocity of light. This constancy of the velocity of light has changed the idea about the universe. Everything is changed now after that. The Michelson-Morley experiment set the stage for Einstein's 1905 special theory of relativity. And for that, he received the Nobel Prize in 1907. Before Einstein's work, a conflict had existed between the principle of mechanics, which were then based on the Newton's laws of motion, and those of electricity and magnetism, which had been developed into unified field theory by Maxwell. Maxwell theory is basically Maxwell equation now. It is a set of 4 partial differential equations which set the basis for describing the electromagnetism, classical electromagnetism. Maxwell, and they are basically these three. He combined 4 theories together. That was the Gauss law of magnetism, and then Faraday law and Ampere law. These 4 laws are combined together, and that is called the Maxwell, because Maxwell did it. And this is the complete electromagnetic theory. We can say unified field theory by Maxwell. Now, Einstein's special theory of relativity, we must understand this idea. This is very, very important. It is basically a guiding force to physical laws. It has 2 postulates. The law of physics is same for all inertial observers, and the constancy of the velocity of light in vacuum. This is a very important thing now, the second idea. Clearly, this second premise, that means the constancy of the velocity of light, is incompatible with the Euclidean and Newtonian concept of absolute space, absolute time, resulting in a program that merged space and time into a single structure with well-known consequence. So now that time onward, a 4th dimension is added in the concept of the space. So it is called space-time now. And 4th dimension time is the 4th dimension, x, y, z, and the 4th dimension is the time. Einstein showed that the Maxwell theory is consistent with special relativity, whereas the Newtonian mechanics is not, and his modification of the mechanics brought these branches of physics into account. Now, due to constancy of the velocity of light, the Galilean transformation is replaced by the Lorentz transformation. These are the technical terms, and the mathematical explanation is already there. So I just avoided all mathematical explanation. Just theoretical ideas I want to give to make it more understandable to all of you. Now, Maxwell equations are invariant under Lorentz transformation. This was the beauty of Maxwell equation. And Maxwell field theory is local and linear now. So locally, valid, and is, nature is linear. Now, the most important thing now, Einstein's general theory of relativity, that must be introduced. The physical foundation of Einstein's view of gravitation, general relativity, lies on 2 empirical findings. that he elevated to the status of basic postulates. And they are relativity principle. Local physics is governed by the theory of special relativity. So in the general relativity, he included the special relativity basically. So local physics, he says local physics is governed by the theory of special relativity that we had discussed right now. And the second very, very important, principle that is called equivalence principle, which says there is no way for an observer to distinguish locally between gravity and acceleration. That means gravity and acceleration cannot be distinguished locally. This is very interesting feature of the principle of general relativity. General theory of relativity is basically a local but non-linear because of the curved space-time. Now the space-time is not linear, it is non-linear. Einstein, through his famous box experiment, first proved that the gravitation is curved space-time. This is very important. Box experiment is available in internet. You can search and you can understand. It will take time to explain that. Thus, in general relativity, a gravitational situation is equivalent to imposing a Riemannian structure on the space-time fourfold. That means now the gravity is nothing but the geometry of the space-time. He related the gravity with the geometry. And he says a gravitational situation is equivalent to imposing a Riemannian structure. He's talking about the Riemannian geometry on the space-time fourfold. There exists a correspondence between matter energy and the geometry of the physical four-dimensional space-time. The mathematical expression of these ideas constitute Einstein's theory of general relativity, one of the most beautiful artifacts of pure thought ever produced. Finally, in the American physicist John Archibald summarized the theory as curved space-time tells mass energy how to move. Mass energy tells space-time how to curve. So this is both are interrelated. Mass energy is related to the curved space-time, and curved space-time, that is the geometry of the space-time, is related to the mass energy. This was a very interesting, interestingly summarized by American physicist John Archibald. And thus in Einstein, this is the mathematical, equation of the Einstein. This is Einstein general theory of relativity equation. This is given in a tensor form. Left hand side is a part of geometry and right hand side is the matter energy. The Tij. This is energy momentum tensor basically. And the left hand side is a part of the geometry, and every terms have their usual meaning. I'm not going inside on this. When you will see my research paper now, everything is elaborated. So this is all about the gravitation and geometry. How geometry of space-time is related to the gravity. This was very interestingly given by Einstein in his equation. Equation number 1 and equation number 2 is basically the part of equation 1. Now I want to come to my second topic, that is the cosmology. How cosmology is related with the gravitation now, and what is the motivation of the cosmological model. This is also very interesting thing. And how cosmology, the idea about the cosmology came into human's mind and human knowledge. This is very important now. So first I would like to discuss motivation to the cosmological models. Cosmology is the branch of astronomy, as we know, dealing with the large scale structure of the universe, extending to distances of billions of light years, and its history and extrapolation of its future course of evolution. The volume occupied by the galaxies is less than or equal to 10 to the power minus 6 times the volume of the universe. This explains why galaxies are treated as a point particle as compared to the whole universe. Traditionally, cosmology has excited the imagination of the religious thinkers, philosophers, and poets, besides its root in the science of astronomy. Our tools of observation and the knowledge of the laws of nature are not good enough and sufficiently advanced to interpret scientific information about the large-scale structure of the universe. And a very interesting remark about the universe by Albert Einstein. He says, the most incomprehensible thing about the universe is that it is incomprehensible. This was a very interesting remark by him. As we could understand the beauty of the Einstein general theory of relativity that I just explained, which is a complete theory of gravitation so far, So at present, it is the only possible theory of gravitation that could be applied to the behavior of large portion of the universe. On the basis of dubious metaphysical predictions, we can choose between universes which are finite and infinite in spatial content. Cosmological principle. This is very important thing to be discussed before we are going to understand the model of the universe, cosmological model of the universe. They are homogeneity and isotropy. Homogeneity means homogeneous. Matter in the universe are uniformly distributed. This is homogeneity. And isotropy, from any part of the universe, you look the universe look the same. So these two terminology are highly used in describing the cosmological model. Both Newton and Einstein considered the universe to be static. In practical terms, there was a major difficulty in arriving at a static model of the universe. Due to gravitational pull, the universe will ultimately contract. To get rid of this difficulty, Einstein introduced an extra term, lambda term, that is called repulsive term into his field equation. When you will see the large, vast Einsteinian equation, and when we translate this tensor form of equation to the nonlinear differential equation now, so this lambda term is highly used. We have to calculate this lambda term also. Now, understanding of the cosmology is not complete without understanding the Hubble's law. Hubble's law, I'm not going deep inside the Hubble's law, but this is the most important law so far for the universe to be understood. According to this law, it is concluded that the galaxies are receding from each other, resulting in an expanding universe. So our universe is expanding, and this law proves this. Now, finally, I want to conclude because I don't want to take much time, So there are several theories proposed by different scientists to construct the model of the universe. Important theories are as follows. So these were the motivation basically. Motivation means just before understanding the models, we are just understanding few important terminology. Now I want to come to the important cosmological model. There are several theories proposed by different scientists to construct the model of the universe. Important theories are as follows. First, Big Bang theory is a well-known theory now, and more acceptable theory, we know this. In so many of my research papers now, we get a result which indicates this Big Bang theory. And then the second theory, interesting theory also, the steady state theory. Third one is the cycle of creation. This is the third theory. And the model without singularity is also possible. That means model which will be more like a Big Bang model, but without singularity, without a Big Bang. Now, about the Big Bang theory, we can discuss one by one. This theory was first proposed by Lemaitre in 1927. He put forward the idea that the universe was once condensed into a single huge mass that became unstable and exploded. He called it the cosmic egg and suggested the fact that galaxies can now be observed receding from each other was the direct result of that original explosion. This theory was strongly supported by the existence of cosmic microwave background radiation, CMBR. In practice, we say CMBR. And we have CMBR data also available, and that we compare our result, whatever result we get in our research paper, we compare with the data, the CMBR data. This is very interesting, which is supporting the Big Bang theory. So more about the Big Bang situation now, we need to discuss. 1,000 millionth of a second after the Big Bang, its temperature was about 200,000 million degrees Fahrenheit. It's a very interesting stage we can observe. A mass equivalent to that of Earth would have been squeezed into a volume no greater than an average sized bucket. It's a very interesting situation. Such extreme conditions mean that the only form in which the matter could exist was in the form of tiny elementary particles. Mass equivalent to our entire galaxy crushed into a volume less than 4,000th of an inch across. Such kind of condition is called quantum era, in which the very concept of space-time ceased to have any meaning. Now the second important theory, this is also in practice, that is a steady state theory, because so many scientists, they got results which support this theory also. This was given by three English astronomers, Herman Bondi, Thomas Gold, and Fred Hoyle. And this is the radical alternative to the Big Bang theory. And the name of this theory is steady state theory. They argued that despite appearances, the universe was unchanging in overall terms. This theory says that, if possible, if people could travel either backward or forward in time, they would still see the universe looking very much it does today. After the detection of CMBR in 1965, the steady theory became no longer acceptable. Now the cycle of creation now. This is the third theory, the important theory. A confusing question always arises in human mind, whether the universe will expand forever or not. Some scientists believe that after another 50 to 100 billion years, expansion will cease and the universe will fall back upon itself, becoming smaller, hotter, and more dense. This is also a very interesting thing. Now the last one, the model without singularity, the fourth model, fourth cosmological model. And it is also in some of my paper I got the result, which is supporting the model without singularity. There is no singularity. There is no Big Bang situation, but it's still, hot and dense space. It is possible to formulate a mathematically simple and attractive model, avoiding initial singularity, while still possessing hot, dense state. This type of model may be possible by inclusion of the second viscosity fluid filling the model. So this is basically all about my, presentation. I have tried to summarize in a brief. And that's all now from my side. Thank you very much.
Thank you, sir.
Thank you very much.
Thank you, sir. Your information will be benefited us in many ways. Thank you so much.
Yeah,
Now let me introduce our another guest of honor and keynote speaker, Professor Zeri Bona, sir, University of Illinois, Chicago. Professor Zeri Bona, sir, is presently working as a professor in mathematics, statistics, and computer science, University of Illinois, Chicago. He did his BS in applied mathematics and computer science from Washington University, St. Louis. He completed his PhD in mathematics from Harvard University. He is known for his work in fluid mechanics, especially water wave theory. He has been an invited longer-term visitor at science centers all over the world. He is currently working with faculty in the bioengineering department at UIC and with faculty in oceanography in New Zealand. He served on the editorial board and also organized many national and international conferences. He got several honors in his academic career by several societies. Few wins are by Fellow of the American Association for the Advancement of Science, by the American Mathematical Society, which is more than 3 times, by the Society of Industrial and Applied Mathematics as an invited speaker, by International Congress of Mathematicians, by American Physical Society, and many more. Now I would like to request Professor Zeri Bona, sir, to deliver his keynote address. Sir, please.
Okay, can you hear me and can you see the screen?
No, sir, not yet. No, sir, not yet.
Can you see that?
No, sir, not yet, sir.
Well, what is it that I'm doing wrong then?
Okay,
I
sir.
asked, hold on a minute. Let me go back to the.
His screen is coming.
Oh,
He is coming on screen.
No,
Yes, sir,
I
it's
see.
not coming.
Unfortunately, there's a button here that says share, but it doesn't do anything. I'm not quite sure what the trouble is. Let me try. Let me just cancel that for a minute. So now, entire screen. Fine. Oh, now that does it. Can you see that?
Yes, sir.
Okay, fine. Okay, so thank you very much for the invitation. It's a pleasure. I've been to India in person many times. This is only the second time I'm coming in on the air. So I'm going to talk about catastrophes, particular catastrophic ocean waves. So if these waves are, I'll show you in some detail, are very dangerous, and we would like, people have been working on trying to understand what they can do about them. So it's very hard to stop a wave in the middle of the ocean, but if you understand how it works, you at least have a chance of making predictions and warnings. So that's what I want to talk about today. This is work with a whole range of people. There are mathematicians, there are physicists, there are oceanographers, coastal engineers, numerical analysts, all in this list of people, and they come from all over the world. Okay, so first thing I want to talk about is tsunamis. Everybody's heard about tsunamis. I'm going to show you a few pictures of tsunamis. Now, remember, these pictures are not taken by professional scientists. They're just taken by somebody who happened to be at the wrong place at the right time. So here's a tsunami coming on board in Hawaii in 1946. You can't really quite tell how big that thing is, but the next picture you get an idea, because you can see it's half the height of a tree, and I'm not quite sure why the photographer is not running. This is the more recent tsunami off the coast of Japan. This is in Sendai, the picture's in Sendai. You can see the wave coming. You can't tell how big that is because you don't have a vertical scale. And you still can't really tell how big it is because you don't have a good vertical scale. But now you can. These waves are coming in half the height of a big building. And it did enormous damage. Here's another picture of it coming on board. So the epicenter was out in the Pacific Ocean, and Sendai was the city that got hurt the worst by this thing. Let me turn now to the one I want to talk about the most. This is the 2004 tsunami, and what you're looking at is the southern coast of Sri Lanka. So you're up in an airplane, so you're in no danger. And I guess the folks up there in the airplane didn't see the first wave coming, because there you see it's already flooded, and they didn't catch the wave. But now the next picture is extremely interesting. You see the water is running out. If you're ever at a beach and the water begins to run out like that, like somebody pulled the plug in a bathtub, you go the other way, because that water is forming, it's part of a wave that's coming on board. That's the trough, and there goes the second wave. This is Thailand. It's the same tsunami that hit Sri Lanka. This is the coast of Thailand, and there you see the tsunami coming on board. And by the way, there at the right-hand side is an American tourist who's not running. Everybody else is. This is also Thailand, but it's a different beach. And now this is instructive. There in the background, you can see the wave beginning to become visible. In the middle of the ocean, tsunamis are not really visible. Not if you're in a boat. If you're in a boat and a tsunami runs past you in deep water, you won't notice it. Well, you might notice it if you know what to look for, but you won't. There's nothing dangerous about it. But as it gets closer to the the shore, we'll talk about this in a minute, it gets larger. And so here it comes. You see the water has run out. The folks there on the beach are picking up shells that they normally wouldn't be able to pick up, I suppose. And here comes the tsunami. Now you don't know how big that is because, again, no vertical scale. But now you do, because that's a person there at the bottom left-hand side. So this enormous amplitude wave, very turbulent. The camera did not survive this wave, but the chip did. That's how we got the pictures. Now, that 2004 tsunami, the epicenter was there by Indonesia. And of course, Indonesia is going to get the worst of it. The countries I've colored in yellow are countries that had severe damage. And my definition of severe damage is somebody died because of the tsunami. So the first question you want to know about a tsunami is how in the world do you get energy across thousands of kilometers of ocean to Madagascar, South Africa, Kenya, so forth. That just why hasn't it just spread out and become nothing to be worried about? And then the second question, these are the estimated death tolls. Of course, Indonesia got the worst of it. I want to call your attention to Sri Lanka and Thailand. Sri Lanka and Thailand are about the same distance from the epicenter. They have about the same coastline exposed to the tsunami. So why is there a factor of 4 difference between the two? That's another question we'd like to understand the answer to. This, they're a big group of scientists who are working on early warning systems for tsunamis, and questions of this sort are very important. Okay, now the 2004 tsunami was generated this way. The plates that make up the Earth's surface bump into each other, and you see the top picture. There's one there that slides under another one, and what that does is it lifts up what I call the continental crust. It's about 18 inches or something like that, not very much. Now, water is incompressible, so what that means is that right away you're going to have a little bump on the surface because of the rising land. That bump, of course, will not stay there because of gravity, so it will spread out in some way. That's the part we need to understand. That's the third picture there. The bottom picture is as the wave gets near the coastline. So in deep water, the amplitude is small. It's 18 inches or something of that sort. But the wavelength is extremely long. As you get to the shore, the depth decreases and the wavelength decreases. And what that does, that water has to go somewhere, so it gets to be much higher wave. So that we understand pretty well actually that run up, the final part of it. That won't be that won't be what we're interested in today. And we understand at least to some extent this generation process. The land rises up and you get a bump of water on the surface. What we don't understand is how you get the energy across thousands of kilometers of water. And we also have this question of Sri Lanka versus Thailand. Okay, so of course, to answer questions like this, you need some water wave theory. I'm not going to go into any detailed water wave theory, by the way, is quite old. The mathematical theory starts with Euler. So this is 17th century. And Euler and Bernoulli, by the time Euler and Bernoulli had finished with water wave theory, we had the water wave problem. Okay, I'm just showing you this to show you it's something pretty complicated. It's been around for order of 250 years, and there's still many things we don't know about this theory. So I won't, as I say, I'm not going to talk about it. I just want to show you what it looks like. Those are partial derivatives, by the way. Now, in the 19th century, in the 19th century, questions about water waves arose, and presumably one can answer them by this theory, but mathematics at that time was unable to tackle anything this complicated. So people created approximations of this very complicated looking model. So this gentleman is John Scott Russell. He was a Scottish engineer. He did various things, sort of a Victorian sort of person with lots of different careers. The thing that I want to focus on was what happened to him in 1834. He was working on a canal in Scotland, and there was a barge that was the way goods were transported in the 19th century, by barges, because the roads were not passable the whole year. So there's this barge, it's heavily loaded, and it's being pulled by a team of 2 horses as fast as a team of 2 horses can pull it. And he doesn't tell us why, but it came to a sudden stop. Presumably a tree had fallen into the canal, and the barge bumped into the tree. What happened was interesting. You generate waves that way. You can do this in your bathtub. Take a flat object and move it through the water and then stop. And you will see you generate waves. I'm going to show you the wave in a minute. Russell was intrigued. He got on a horse and chased the wave that formed, and chased it for something like 3 kilometers as far as we can tell. What he noticed was it moved at constant speed and constant shape. So he thought that was interesting. And here's this is fanciful, by the way. This is his drawing of the event. But you see a team of 6 horses, and it wasn't 6, it was 2. Nevertheless, it's a nice picture. He did over a period of a decade, he did experiments in water tanks, trying to figure out things about this wave. Here you see on the right-hand side one of his experiments. He has a tank full of water. He drops a block into one end of it. That's supposed to simulate what the barge did to the water in the canal. And you see this wave forming and moving out at constant speed and constant velocity. So Russell had lots of nice names for this wave. He called it the Great Wave of Translation, the Primary Wave of First Order. He also called it Solitary Wave. It was a solitary wave because it didn't have any neighbors. Okay, that's the name that stuck. So these experiments were known throughout the 1830s and early 1840s. And in his final report to the British Association of Science, he throws out a challenge. He says, okay, guys, you mathematicians, I found this wave. Now you guys should go back to your equations and find it in your equations. So he was challenging the mathematicians to find his solitary wave. And okay, this, by the way, is part of the canal that joins Edinburgh to Glasgow. And this is an experiment that we did at a conference some years ago. This is a particularly good part of the canal because it's under control, narrower than the rest of it. We didn't have a barge. We did have that little boat you see there. And the first time we tried this, we were unsuccessful. And the reason we were unsuccessful was we didn't have enough weight in the boat. So the second time we tried it, we loaded it up with graduate students. And there you see the wave. So what you do is you run the boat full speed, and then you hit reverse on the motor. That's not very good for the motor, but you see the wave that's coming out there. It's a long crested wave, and sure enough, it moves at more or less constant speed and constant velocity. Airy, Sir George Airy, the Astronomer Royal in Britain at the time, took up Russell's challenge and wrote theory and decided that there was no wave of permanent form like that on the surface of water. And just to give you an idea, Airy was a big shot. People knew about Airy. I mean, he even has stamps. Very few mathematicians have stamps. Well, you may say these are stamps in funny places, but you know, Britain owned the world in those days. They even parodied him in popular magazines. So he was a very well-known man, and he said Russell was wrong. That is Stokes of Stokes' theorem. That's the young Stokes. This is an older Stokes. He's now Sir George Stokes, another knight of the realm. He also wrote theory, and he also said that Russell was wrong. There was no wave of move at constant speed and constant shape on the surface of water. So this was in the 1840s. So there the situation lay. Russell had seen it, had done experiments with it. Two of the best known scientists of the time had mathematical theory that said it didn't exist. So what went wrong was corrected, but only much later. The one who gets the credit most of the time is Joseph Korteweg, a Dutch mathematician, his student De Vries, who I don't have a picture of at the moment. But in fact, Boussinesq, a French mathematician, beat him to it by about 20 years. The trouble was Boussinesq wrote this up in a paper, it's a memoir really, it's over 600 pages long, and it's the part where he gets to this point is buried in a footnote that goes on for a page. This is the theory, and again, I'm not going to talk about the mathematics, but you can kind of tell that this is a whole lot simpler than that set of equations I wrote earlier. Okay, and okay, let me tell you what the variable is here. If you're looking, I'm now looking at a water tank again. You'll see this picture again. So X is an independent variable, and it tells you where you are in the channel. So X equals 0 is over there near the wave maker. X equals L, say, is the end of the channel. And then T, of course, is time. And eta is the deviation of the free surface above the point X at time T. That's the dependent variable that you're trying to predict. Okay, now I think I'm not going to go through the derivation of these equations. If you're going to make an approximation, you have to decide what kind of waves you're talking about, and different types of waves have different approximations. There's a whole scheme for these kinds of approximations that you see sort of outlined here. We won't go into those. This is more or less the equation I'll use to explain the tsunami. It's not two equations, it's actually three. Capital V is a vector. Okay, so let's not look at that. Oh, this whole scheme of approximation has kept applied mathematicians and mathematicians busy for several decades now, trying to tell how good the model is theoretically, and of course also you'll see in number 6 there, experiments as well. So let's look at some experiments just to give you an idea. So these experiments are done in a wave tank. At the far end of that tank is a piston type wave maker. You see some measuring devices on a trolley there on the top of it. And the experiment is like this. At time 0, everything's at rest, and you turn on the wave maker. And you're controlling two things. You're controlling the frequency of the oscillation and how big the oscillation is, the amplitude of it, if you like. Those two parameters translate into the wavelength of the wave, that's related to the frequency, and the amplitude of the wave, which is related to the amplitude of the oscillation of the piston wave maker. And then you're taking 4 measurements downstream. Now these, you have to be careful. These are measurements at a single point as functions of time. So these are temporal traces. You're measuring those 4 temporal traces, and you take your model and you use that first trace, the one that doesn't have a letter above it, as boundary data. That's the input, and the initial data is 0. It's not moving at all. It's at the start, and then your model is meant to predict what happens at A, B, and C. And then of course you take the measurements at A, B, and C, and you just lay them on top of each other. So there's no free parameters here. There's no fitting going on. You're just checking the model. Okay, now that is typical boundary data. So remember, that's the water going up and down at that point. At that point, with the first, we'll call it x equals 0. That first measuring device. Okay, so that's what your input is into the model, and here is the comparison. The first comparison. This is a relatively mild wave, and you see the stations down the channel. The top one is what I called in this picture A, and the second one is B, and the third one is C. You see the wave is getting there later, of course. And what you're seeing, you see the diamonds, those are the measurements, and you see a line that you can just make out behind those diamonds. That's the output of your computer code, which is generated by the model. So you see it's working very well, but that's a fairly simple looking wave. It's not as simple as you think. This is what the computer thinks is in the channel. Not quite so simple as what you thought. But much more interesting is we did lots of experiments, 20 or 30 experiments. This is a wave that's not so far from breaking, and you see that at the station A there, it's already it looked at the initial station, it looked just the way I showed a minute ago, but at the station A, it already has a secondary crest. Now that secondary crest is underneath the primary one. At station B, and at station C, you can just begin to see the model diverging. On the other hand, my engineering friends said, "Oh, spot on." so these are the kind of results. There are other. Oh, this is, by the way, this is what the computer thinks is in the channel. So you see that top wave there. It's a fairly complicated waveform to generate that kind of agreement. Okay, now let's go back to tsunamis and try to answer our questions. Okay, so remember there are two questions. One is, how in the world do we get energy across all that distance? And secondly, how come Sri Lanka got hit worse? Okay, so let's look at this. We're going to use one of those three-dimensional Boussinesq systems that I flashed up a moment ago. Now, I should have said something about solitary waves. The reason why we have these waves of permanent form, the waves that just propagate at constant speed with no change of shape, is because of a balance between two aspects of wave propagation. One is a nonlinear effect, and the nonlinear effect is what you see at a beach. When you see a wave coming in and breaking, that's because of nonlinearity. And the reason it's breaking is because the depth is getting shallower and the nonlinearity is getting stronger. So there's always nonlinearity out there. The other aspect of wave propagation is dispersion. Dispersion spreads waves out. You can see dispersion in your bathtub very easily. Put a light over it so you can see the shadows of the waves, and make a point disturbance. And you watch the waves coming out, and what you'll see is that different wavelengths come out at different times. This is dispersion. Different wavelengths travel at different speeds. Solitary waves exist because the nonlinearity and the dispersion can balance. Okay, so let's do a simulation. I'm going to start with a heap of water. You see what it is. It's a Gaussian. And be very careful. My vertical scale there is a fraction of a meter, and the horizontal scale is many kilometers, hundreds of kilometers. So I have to keep those scales separate, or you can't see the disturbance. So here's the disturbance, and I'm sticking that into that model that I showed you a minute ago. There it goes, and now you see what's happening. The nonlinearity and dispersion are balancing, and you're keeping the wave is staying together. It's not just spreading out. Okay, so that gives you an idea of how you can get energy across such vast amounts of ocean. However, if you look at that picture, one direction is Sri Lanka and the other direction is Thailand, the two orthogonal directions there. And I don't see any difference in the wave that's getting there. So what did I do wrong? And the answer is, let me show you. I started with a circularly symmetric bump. A much better approximation of the real bump that gets formed is an ellipse. A very long, very different semi-axes. So I started it off with very different semi-axes. Now you can look up there and see that I've used a factor of 16 as the difference in the semi-axes. Probably it's even worse than that. And now you see it's the same model, but the initial data is elliptical instead of circular. And you see quite a different structure. First of all, a lot of secondary crests. A lot of those would be hit by dissipation, would be gone. They wouldn't actually be there. And now, okay, so now you see why there might be these second waves or sometimes even third wave. But also, if you look at look on the axes at the two places that are marked 60, you'll see that one of them is about 4 times bigger than the other. And what the cause of that is that the angle of the plates that push together and lifted up, Sri Lanka is right ahead is straight ahead, and Thailand is off to the side, and that's why you got that big difference in the death toll and destruction too, by the way. Okay, now I'm going to switch gears. I don't know how much of this I'll get through, but let's see how I'm doing. I want to talk about rogue waves. These are also called giant waves or freak waves. Sailors used to come in from the sea and talk about waves that were 50 feet high, and nobody believed them. You know, it was like the fish that got away. But you know, lately we've had cameras and things like that. So let me show you. So this is the North Sea. It's, as you can see, it's not a stormy day at all. That's a very typical North Sea. Actually, it's a mild North Sea, except for that grade. And here it comes. So that's a pretty big wave. There's a ship going into the trough of a rogue wave. Ships don't do very well when they get out of the water like that. They're not made to be flexed. They're very good at taking pressure inward, but they're not made to be flexed. We'll see in a minute. This is a rogue wave in those two are rogue waves in deep water. This is a rogue wave in shallow water, relatively shallow. There's another one in shallow water, and another one. These things are very different from tsunamis. A tsunami propagates thousands of kilometers, can propagate thousands of kilometers. Rogue waves seems to come out of nowhere. They form for a while, they propagate, and then they're gone. They exist only in a sort of a region of space-time. So, oh, here's a boat that didn't do very well with a rogue wave. That was an aircraft carrier. One rogue wave did that. And there's a oil platform that didn't do so well either. Now the question is, where do they come from? So here's field data. This is really the only field data that we have. This was the Norwegian oil platform. It's New Year's Day, 1995. And they happen to have instruments in the water even though it's New Year's Day. And so you see if you look closely there, you see it's fairly rough seas, about 5-meter waves. And then all of a sudden there's that one that's about 30 meters, trough to crest. And it's probably bigger than that. The instrument's probably saturated. They're just not able to measure anything bigger than about 30 meters. And then it's gone. There's no more. It went back to the same structure it had before. So this is what we're trying to understand. Where did that come from? And there's some theories. First theory is what I call concurrence of various types. So what does concurrence mean? Well, if you look out at the ocean, you're up in an airplane, you look at the ocean, there are waves everywhere. There's a vast amount of energy out there, just not focused. In fact, that's been one of our big problems with trying to get energy out of waves, is that the energy is there, but we can't get our hands on it because it's too dispersed. Okay, so what concurrence says is that, well, there's all that energy, and maybe every once in a while, some of it gets together and has a party, and you get a big wave for a while, and then it comes back apart. There's some other ideas around there. Topographical forcing, of course, wouldn't apply to deep waves, deep water roadways. It would only apply to shallow water roadways. I won't. I could tell you about all of these, but I won't go through that. Let's talk about concurrence. So the question is, does surface water wave theory support the idea of a small wave, small amplitude everywhere wave becoming suddenly big, or not? Okay, so actually, when we were first looking at this, our goal was to prove concurrence could not occur. However, we were wrong. Now I'm going to just this is done by Fourier analysis, and I'll show you just a tiny smidgen of how this works, and I'm doing it in the context of the Schrödinger equation. So this is the linear Schrödinger equation in d dimensions. D is 2 or 3. U is a complex valued function. I is the square root of -1. But it's the real part of U that tells you what the wave is doing. So the solution of that you can work out. It's a linear problem. Fourier analysis gives you the solution. You see it written there at the bottom. It's an integral over the whole of space of a function, an exponential, times the initial value. Phi is what was there initially. Now, the question is, how could I choose initial data so that this linear equation, which will start out, let's say, small, can be big at near some point at a later time? And a little bit of thought gives you an idea. Let's take phi to be this. Phi is the initial data. We'll take it to be this function. It's the exponential. That exponential, since it's imaginary argument, is absolute value 1. And so the 1 plus y squared over to the mth power is there to make the function have finite energy. So this function is infinitely smooth. It's uniformly bounded, and it has finite energy. It's square integrable. Okay, fine. Now let's stick that into our formula. There it is. Okay, and now that's the solution. Now let's see. Think about what happens when y is large, either negative or positive. When y is large, those two exponentials, they're basically sines and cosines. They oscillate like crazy, right? Faster and faster. And there's enormous cancellation. And so that function u is a nice smooth function, solves the equation. Okay. It does, except suppose I took x equal to 0. Then it's e to the I absolute value of y squared over 4t. And suppose I took t equal to a quarter. Then it's e to the I absolute y squared times e to the minus I absolute y squared. All that oscillation cancels out. And you're just left with this. Right? At x equals 0 and t equal a quarter, you're left with this. And it turns out you can choose m. M, remember, just a parameter. You can choose m between the dimension over 4 and the dimension over 2, such that the solution, the initial value starts out in this nice space, but the solution actually doesn't just get big, it actually blows up, becomes infinite at the point 0 1/4. And since it's a linear equation, this is self-improving. You can multiply that initial data by any small number and it'll still blow up. So this will be initial data that starts off, maybe a centimeter high. The amplitude of the wave is a centimeter, and in finite time, at a particular point, it will become infinitely large. That might be a reason to think of a rogue wave. That's concurrence. That's what that is, in fact. Now, the problem with that is that I used the linearity to solve the equation. And of course, actually, it was our idea that nonlinearity would spoil this picture. Let me not go into that. Okay, I won't go into that either. Now, if you add nonlinearity, so you see this epsilon times u to the p, u equals 0. Remember, u is complex. P is an integer. And in fact, the water wave problem occurs when p equals 2. There's the mathematicians among you will know what I'm talking about. Nobody else will. There's a Duhamel's formula allows you to solve that kind of equation. You see u equals what I call S of t onto u0. u0 again is the initial data, and S of t is nothing more than what we wrote down a minute ago. This integral. Okay, so it's that integral. Okay. So that one we understand. We've already figured that one out. The other term is much more complicated, but it has the same kind of exponential in it. Now, we can choose u0 in such a way that S of t u0 blows up. We just did that. The question is, is there some way to tell that second integral, which is a double integral, is actually continuous? And that's the answer to that is yes. That function, because of the time integration, you're integrating not only in space with respect to y, but also in time. And because of the temporal integration, that second integral is continuous, which means that the solution u blows up just like the original one that we saw. So our conclusion, which wasn't what we thought to begin with, is that indeed you could have concurrence, and that might be one of the routes to a rogue wave. I think that's my time used up. Thank you very much for your invitation and for the attention.
Thank you, sir. Your presentation and lecture is totally according to our conference theme. All of us get huge amount of information through your lecture. Thank you so much, sir.
Certainly. Okay, time for lunch now.
Thank you, sir. Same here. Thanks a lot, sir. I regret to inform you all that President of the conference, Yuvraj sir, and Vice President, Professor Pankaj Gupta, sir, are stuck in an unavoidable professional matter. Therefore, they are unable to join us in our inaugural session. Now we are at the end of our inaugural session. I would like to request co-coordinator of the conference, Dr. Amit Kumar Singh, to deliver vote of thanks. Sir, please.
Ma'am, am I audible?
Yes, sir, you are audible. Yes, sir, you are audible.
Thank you very much, ma'am. Myself, Dr. Amit Kumar Singh, and I deem it a great honor and privilege to propose the vote of thanks on this memorable occasion of International Conference on Advances in Applied Sciences, Humanities, and Technology to Overcome Global Disasters. A very good morning, all of you present here. First of all, I wish to thank the Almighty for giving us strength in fulfilling this conference. Actually, International Conference is a platform to share latest and innovative ideas with peers and senior group of people from different parts of world by the help of a PPT or poster presentation. Our conference undergoes with a pre-registration process by highly qualified editorial board and organizing committee who takes the decision after reviewing the received abstracts and topics for the presentation. Most of this process is processed with a blind peer review process. After registration, the organizer informs about the venue and schedule to the attendee. I am glad to inform you all that researchers and faculty members from all over the world participate in this conference with their excellent quality research. First and foremost, I must mention our deep sense of appreciation to Chief Guest Professor R.K.S. Dhakre Sir, Vice Chancellor, MS Bridge University, Bharatpur, for kindly accepting our invitation and gracing the inaugural function. I am also thankful to Guest of Honor Dr. Ashok Yadav Sir, Chairman IEI, for his inspiring association. I am also thankful to IEI administration in general for providing us with all possible logistic supports towards organizing this event. We are especially thankful to Yuvraj Amrish Pal Singh Ji, Secretary, Balwant Education Society, who amid his heavy burdens, duties and responsibilities to dignify and magnify our meeting here today. Many of dignitaries who are also sharing their time with us in this event have also changed previously commitments in their social and professional duties to find time to render stimulation and appreciation to the international scientific community represented here by scientists from different countries from all over the world. I sincerely thank to our keynote speakers, Dr. Mohammad Ziauddin, Sir, Jewel Industrial College, Saudi Arabia, and Dr. Jerry Bona, Sir, University of Illinois, Chicago, for an enlightening and entertaining presentation on how to promote international research with a global perspective to understand the generation mechanism of low probability but high consequence global scale natural disaster. We really appreciate that. Thank you, sir. I would like to thank Vice President Vice President Professor B.S. Kushwaha, sir, Director Raja Balwant Singh Engineering Technical Campus, Bigpuri, Agra, for infusing confidence and a sense of excitement and inspiring us in our work through his encouragement and guidance. My sincere and heartfelt thanks to him for his valuable suggestions. I am also thankful to Vice President Professor Pankaj Gupta, sir, Director Administration and Finance, Raja Balwant Singh Engineering Technical Campus, Bigpuri, Agra, for providing us with all possible logistic support towards organizing this event. I give my special thanks to Dr. S.P. Pandey, sir, coordinator of this international conference, who always stand by us, guide us, lead us, and motivate us. Sir, your words of wisdom radiated a source of energy within us. I will ever remain grateful to you, and I thank you for being with us today. I would like to extend my sincere thanks and regard to Professor A.V. Lal sir and Dr. Ashish Shukla sir, who have blessed us with their presence. I am very much thankful to Professor Sapna Tomar ma'am and Dr. Syamir sir for operating and handling YouTube activity during the whole session. I am always be grateful for it. Thank you so much. I would like to thank the organizing team who have given enormous support to make this program successful. At last, but not the least, it has been our pleasure to host all participants of the conference. I am thankful to all the participants for attending the conference. We have been fortunate to have some of the eminent persons from academia, industry, and utility working in the area of power system. I am sure that the participants must have benefited by attending this conference. Thank you all for your support. Stay home, stay safe, stay blessed. Thank you very much.
Thank you, sir. Thank you all for joining us in the inaugural session of this international conference. We will rejoin here through the same Google link for our first technical session, which will be held today from 12:30 p.m. onwards. Till then, thank you and have a nice day ahead. Thank you all.